Let's get started with question 115, distinct subsequences. Given a string S and a string T, count the number of distinct subsequences of S which equals T. A subsequence of a string is a new string which is formed from original string by deleting some, can be none of the characters without disturbing the relative positions of the remaining characters. That is, ACE is a subsequence of ABCDE. Why? Well, we can form ACE as A, then C, then E. So the positions, the relative positions are still same. While AEC is not a subsequence, that is A, E and C. So we are disturbing the relative positions, so AEC is not a subsequence, where ACE is. It's guaranteed the answer fits on a 32-bit signed integer. Okay, so let's jump right into the question now. Now we have two strings here, S and T, and these are the corresponding indices of the characters. Now you must be thinking, what is this weird structure drawn here? So I will explain it in a bit. So what we are actually going to do here is use recursive approach along with dynamic programming to store the results of the states which we have obtained so that we don't calculate it again and again. So let's jump right into this solution now. So the crux of this solution, that what are we actually doing here, is first of all passing the starting index of both the strings, that is where we have to start in string S and where we have to start in string T. So we are initially starting from 0, 0, that is starting index for both the strings. Now we will check if the characters on those indices are same or not. If they are not, then we are actually in a for loop, so we will iterate through each and every character in string S in one recursion, but we will not change the value of j in a single recursion. The value of j will only be changed here. Now what is this actually? For example, here we have same characters at indices 0, 0, that is 0s here, there is r, and 0 T here, there is R. So at starting indices 0, 0, we have same characters here. So as we have same characters on the given indices, we will move forward in recursion as setting the starting indices for next recursion as I plus 1 and j plus 1. That is the indices on which we found the same characters. We will increment that index, both the indices by 1, like not in place. We will send I plus 1 and j plus 1. We want I plus plus, that is I won't be equal to I plus 1. We will just send an increased value, that is I plus 1 and j plus 1 to the next recursion. That is, in the next recursion for A in A here, the starting index will be 1. That is, we will be starting from index 1 in S as well as index 1 in T. So now let's see what's happening here. For start, we are on index 0, 0 initially. We see that these two characters are same, so we move ahead in recursion. So then we are on 1, 1. So we see that we will move forward in recursion as 0 plus 1 is 1 and 0 plus 1 is 1, I comma j plus 1. Yeah, so we are here on starting indices 1 and 1. So we have moved from this recursive step to this recursive step. Now at 1, 1, we see that if the characters on the indices are same. So at 1 and 1, yes, the characters are same. So we move forward again. We move to 2, 2. Now we are on 2 and 2. We see that the characters are different here. So we increment I in S by 1. So we are on here now. So B and B here. So index 3 here, the character at index 3 here and character at index 2 here are same. So we will send 3 plus 1, that is 4, and 2 plus 1, that is 3 in the next recursion. So you can see it's 4, 3 here. We move on to the next recursion. Now we are on 4 and 3 here. We see that the characters are same. So we again do I plus 1 and j plus 1 and move to the next recursion. We are on 5, 4 here now. Now at 5, 4, we see that the characters again are same. We move on to the next recursion, 6, 5. We see that in 6 and 5 the characters are not same, so we increment the I in this recursion by 1. So we now check 7, 5. We see that the characters are same, so we move on to the next recursion here, 8, 6. Now we have reached the last, like we have exceeded the indices of these string t. That is, now our j is equal to 5 plus 1, that is 6. So when j reaches, that is j is equal to the length of t, that means we have iterated through every character in t. And why do we iterate through every character in t? When there is a corresponding character in s. So if there is a corresponding character in s for every character in t, so in this way, if we move on to the last index, that is j is equal to the length of t, then we know that every character in t is in s at least once. So you can see here that RABBIT, every character in t is present here at least once. So there is a corresponding character is s for every character of t. So when we are here, we will return back 1 here. Now what does this 1 mean? This means that when we are on 6, 5, then if we move ahead in recursion, then we will get one subsequence for this string t, t. So the starting indexes are 6, 5, this 6 and 5. So sorry, we are on I here, I and t, and in string t we are on t here. So if we move forward for this recursion here, we will get one subsequence in the future. So we will return and when we reach the length, that is the length of t here, the j is equal to the length of t, then we know that we have one subsequence. So we return 1 to 6, 5. So the value at 6, 5 will be 1. So this means that if we are on 6, 5 and move ahead in recursion, we will get one subsequence. Now we are on 6, 5, so we check 7 and 5 are equal. Then we move I ahead, as there is no index for I, that is I has reached its limit. We will move back in recursion. So we will take this one with us and also return this one to this 5, 4 here. Now 5, 4, the value in recursion is 1. There is a variable that's storing these values. So now we are on 5, 4 again, that is this and this here. So in this 5, 4 recursion, we check if the character at 5 is equal to character at 4. Then we check for the next character itself again. So we will check if from 5 we move to 6. So we check if the character at 6 is equal to the character at 4. Because j is always constant, we will only be iterating I. So is character at 6 equal to character at 4? Yes. Then we move ahead in recursion again. So we move from 5, 4 to 7, 5. That is 6 plus 1 is 7 and 4 plus 1 is 5. And our characters at 7, 5 equal? Yes. So we move to 8, 6. We have j is equal to the length of t. So we return 1 here. So 1 will be returned here. And similarly, as we have reached the end of string s, 1 will again be returned here. And this will be summed up in the already present value here. That is, we return 1 from here and we return 1 from here. So this value will now become 2. Then we return then we iterate through 5, 4 again. So we are on 5 and 4. We move to 6 and 4. We will then compare 7, 4. Are characters at 7, 4 equal? No. Then as we have reached the end in S, we move back in recursion to 2, 2 and pass the value itself again. Then on 2, 2, that is this here, we move ahead in I. So we will see that this character here is B. Actually we already checked this here, B, B. So yeah, actually I missed some recursions here. So what will happen now here is we have already checked this index 3 with 2 So the result was 4,3. So that is here. Then we will again check. We will move ahead in S and we will check if index 4 here is equal to index 2 here, the characters. So yes, they're equal. So we will move forward in recursion as we checked index 4 here and index 2 here. So we'll move forward as recursion 5, that is 4 plus 1, and here 2 plus 1, that is 3. So we are on recursion 5, 3 here. Okay, now for 5 and 3, we will check if these characters are equal. So is there a B from 5 to 7? No. So we will iterate through the entire string here. So is 5 equal to 3? No. Is 6 equal to 3? No. Is 7 equal to 3? The characters, I mean the characters. So no. And then we reach the end of S. So now what we are actually going to return is 0. Because we haven't found any substring, so we have reached the end of this string S. And when we reach the end of string S, and we still haven't reached the end of string T, so J here is still equal to 3, but S here will become 8 as we keep iterating it in string S. So this will become 8 and this will become this will be equal to 3 only. So we have reached the end of S but not the end of T. So on that condition, on that note, we will return 0. So we will then return 0 from 5,3 to here. So this value 2 will be totally unaffected. So 2 plus 0 is equal to 2. And then for 2,2 here, 2,2 again we will iterate through the entire like 3,2 here, actually yes. So we'll iterate through the entire string S and we'll find out that none of the character matches. So we will then return this value 2 to 1,1 here. Now 1,1 equals 2. So we are on 1 and 1 here. We checked that these two indices are same, so we moved in this recursion. Now we will move ahead in S to this. Now we will see if character at 2 is equal to character at 1. Yes. Now the entirely same story repeats here, that we move from 1,1 to 3,2, that is we are on 2 and 1 here, so we increment by 1 here, so 2 becomes 2 plus 1 is 3 and 1 plus 1 is 2, so 3,2 here. Then from 3,2 we are on 3 and 2 here, we check that the characters are equal, then we move ahead in recursion again. From 3,2 we move to 4,3 and then we move to 5,4. Then you can complete the cycle yourself. So we move to 8,6, then this 8,6 will return 1 and 1 here at both positions. Then this 1 will come up here and become 1, and then this 1 will add up to the 1 here and become 2. So 5,4 will equal to 2 again. Then this 2 will be returned here, that is 4,3. So we are on 4 and 3 here, yes. Then we again move back, then this 2 will again be returned here at 3,2. Now when we move back, this 2 will be added to the already present value in 1,1. So what is the value in 1,1? That is 2. And we add 2 here, so this 2 will become 4. And then as our we checked first is A equal to A, and then we move ahead. Then we checked if this second A is equal to this, and then we move forward again. So we will then move on to this recursion and check if R here is equal to R. We have already checked this. Then is A is equal to R? No. And then we will move ahead in the entire recursion, and we will in the last see that this R is not present in this remaining string. So we will go out of this recursion and the final answer here will be equal to 4. So you can actually see this for yourself, that I and I here, there are 2 I's and 2 A's. So if you apply some permutation and combination, you can calculate the answer as 2 into 2, that is 2C1 into 2C1, that will be 2 into 2, that is 4, and our answer is 4. So we get our expected answer. Now you can see that we have repeated these steps here. That is, recursion 4,3 comes here as well as here. Then recursion 5,4 comes here as well as here. Then recursion 6,5, 6,5, 7,5, 7,5, 8,6. So what if we stored the value of recursion 4,3 somewhere, so that when we reach to 4,3, we won't have to compute these recursions, and we would just get the value 2 from 4,3 and then return it back to this recursion 3,2. It would return it back to 1,1, and then the cycle will continue, and then final value we will get as 4. So what if we stored these values that we calculate in the recursion? So we will be doing exactly that in dynamic programming using memoization. How? Let's see. First of all, we are on 0, 0. So 1, 2, 3, we will move inside the recursion till the last step. Now this DP here is of size, that is, this here is the length of T, and this here, the rows, is the length of S. So how is this working? Let's see. We are on 8, 6. So 8, 6 will return 1, 2, 6, 5 as well as 7, 5. So let's see where are 7, 5 and 6, 5. So it will be 7, 5 will be somewhere here. 7 and this is 5. This is the last value actually. So yeah, this will be equal to 1 now. We have 1 here, and 6, 5 is also equal to 1. So this is this value, that is 1. Okay, now we come back to 5, 4. We got that the 5, 4 value was 2 here. So we are moving back up in the recursion and storing the corresponding values in DP. So 5, 4 is 2 here. So we will check for 5, 4. 5, 4 will be this value here. So this will be equal to 2. Then we again move back in 2, 2. So in 2, 2, we go back to here, 2 and 2 here, and we will store 2 here again. From this 2 to this 2, we will store the values we calculate from the recursion. Also, yeah, we will store this value 4, 3 equal to 2 also. So this 4, 3 will be here. So this value will also be equal to 2. Yes. Okay. And 6, 5 is here. 8, 6 is not calculated. These two values, then this, 5, 4. Actually, we haven't stored anything. At 5, 4, this will also be 2 here. Yeah. So we have stored all the values here. Now we will also store the value for 5, 3 is 0, because we will also be going in that recursion. So we will store the corresponding values in DP. So 5, 3 will be somewhere here, and 3 is with this. So this will be equal to 0. Okay. So now we have some values in DP. This actually what this -1 indicates, that we have not visited this recursion, that is I, j. Recursion, this DP will be in the form I, j, where I denotes the starting index of S and j denotes the starting index of T. So what the DP will be in the form I, j. So we will, as we go back to this 5, 3, we will store the value that we calculate from 5, 3 at index 5, 3 itself, and then we move back. We store 2 and 2, 2. Then we move to 1, 1. Now we will currently store the value 1, 1. So here it will be 1, 1. Yeah. So now from 1, 1, we know that we will go back again in this recursion deep till 8, 6. But we now won't have to go till 8, 6. Why? Because from 1, 1 we come to 3, 2. Now 3, 2 here, this is -1. So we have not yet visited 3, 2. So from 3, 2 we will go in deeper to 4, 3. Now here you can see this 4 comma 3, actually 4 comma 4, this will be minus 1 only, this here will be equal to 2. Yeah, so we will go to 4 comma 3, 0.234 and 1 2 3 here. So this value here, so we already have the value of 4 comma 3, so we don't need to get in deeper to 5 comma 4, 6 comma 5, 7 comma 5, 8 comma 6. We don't need to calculate these. So as we get that this value 4 comma 3 is equal to 2, we just return back to 3 comma 2, and then at 3 comma 2, that is here, we store this value 2, and then at 1 comma 1 we store the sum of the values we get from recursion 2 comma 2 and 3 comma 2, that will be equal to 4. So this value here will be equal to 4, 0 comma 0 will also be equal to 4, and this, the final answer we will get here will be equal to 0 comma 0. Now can you guess why? Well, we have to guess how many substrings that are equal to t are present in S, and that we will be checking from the starting index of both S and T. So from starting index of S, how many such subsequences we can get such that those subsequences are equal to T. So as we will be starting checking from the starting index itself, the TP value which will be present at 0 comma 0, that is starting index for both S comma T, will be the final answer, will be our final answer. So that's the common understanding behind this question. Now let's code it. First of all, we will be creating a DP matrix using vectors, and second, we will call the gen that will generate our output, that is the recursive function. We are passing the two strings S and T and the starting indices here, and this is the DP matrix B here. So also we need to pass the DP matrix by reference, because we need to use the common DP matrix across all the recursions. So either we can pass it by reference or make it global, so everyone can access the same DP matrix, and we will be updating the values in the same DP matrix all over the program. Then we will check if j is equal to the length of t. So if j is equal to length of t, we now know that j has been iterated through all the characters of t, and so it has reached the last character, so there must exist at least one subsequence, so that's why we return 1. And if I is equal to the length of s before j is equal to the length of t, so that means I has reached its end before j could, so there is no more subsequence left, so we return 0. That is, there is no possible subsequence for this case. Then we check dp. If dp I comma j is not equal to -1, then we return dp. So we check if the dp I comma j, that is the state I comma j, has already been iterated. So if it has already been iterated, so its value will be anywhere from between 0 to anything, and if it has not already been seen, the state has not already been seen, so the value will be equal to -1. So if the value is not equal to -1, that is, there is some value stored in dp, so we return it itself. Like here we returned 2 when we reach 4 comma 3 and did not recurse forward anymore. And when we reach 3 comma 2, the value was still -1 because we never encountered 3 comma 2 here anyway. So from 3 comma 2 it was -1, so we move forward and then we return 2 from here because 4 comma 3 was already seen before. Then we define a variable total which will store the total number of subsequences for this current state I comma j. Then we define a for loop which will iterate through every index starting from the starting index of S to the end of S, and for each index it will check if the index of I is equal to the starting index of string t, and if they are equal, we know that we will move forward in recursion. So that is this here, this recursion function is again called, else we will just skip that character, and then at the end we return the value of total which is stored in DP matrix as well as simultaneously returned from the function. So that's how we store the values in DP matrix from this, and we will be using DP matrix to get the already calculated result from here, and in this way this function is written. So that's for the code. There is also one iterative approach, so you can try that for yourself using tabulation. That is also a dynamic programming approach, and it is done using tabulation. So you can either use this recursive approach using memoization, or you can use the iterative approach using tabulation. So that's for this question. Hope you understood this approach, and thank you.